my name is Vanessa Metcalf, and I am a software development manager at Amazon Robotics. Today, I'm going to be talking to you about how Amazon can accelerate the development of manipulation robotic systems by leveraging Gemini, which is an AR-developed robotic modeling and physics-based simulation tool. Before we talk about the details of Gemini, let's frame the problem we're trying to solve. Amazon's constantly looking for ways to improve our fulfillment processes to get orders to customers more efficiently. Robotic manipulation solutions can help us by automating the count, pick, and stow processes throughout Amazon's facilities. Traditionally, complex robotic manipulation solutions have been developed on prototype hardware, with software engineers writing code against their physical systems. While this approach can be very effective, it's often slow and not scalable for the varied types and configurations of robots Amazon develops. There's just simply not enough time or hardware available for everyone on a project team to keep testing their solution on physical hardware until they get it right. It's also impractical to physically test our robots against the tens of millions of different objects that they may need to handle in any given Amazon facility. To keep up with Amazon's growing investment in robotic manipulation, development teams need tools that allow them to develop virtually so that they're not reliant on hardware. In order to be value added, these tools can't just be virtually realistic. They also need to have accurate physics. There really aren't many simulators that are both visually accurate and have accurate physics. It's also important for us to understand and have access to the governing equations so we can analyze and control the robotic systems we build. If the gap between our physical systems and our simulated systems is too large, then the benefits are greatly reduced. It's important for us to address the sim-to-real gap and close it as much as possible. To address this challenge, Amazon Robotics developed Gemini, a robotic modeling and physics-based simulator that enables simulation-first development. Our goal is that all of our robotic research and development starts in simulation. When an Amazon developer has an idea, their first reaction would not be to order parts. Instead, they would use Gemini. They could develop an entire robotic work cell virtually, with a final safety check occurring on hardware. So how does Gemini speed up development exactly? Gemini simulates real-world robotic work cells using the same inputs and outputs as real hardware. This enables teams to develop software in a virtual environment, thereby eliminating hardware wait times and mitigating the impracticalities associated with physically replicating every work cell configuration. Gemini also enables teams to speed up time-consuming design explorations by reducing the reliance on hardware and allowing various solutions to be evaluated in parallel virtually. Gemini also facilitates an increase in overall software quality through virtual testing of each software release. Finally, Gemini leads to an improved performance of fielded robotic solutions by providing tools to developers that allow them to simulate edge cases in error conditions. So how does Gemini do this exactly? To achieve this vision, Gemini needs to create models of the complex robots and also model the objects they're going to interact with regularly. So walk me through an example of what that means. Gemini clearly needs to model the robotic arm, but we can't just stop there. We also need to model the pneumatic gripper with multiple suction cups on the end. Getting into the details of what that means exactly. Gemini needs to model the flow of the air through the gripper's tubes and valves, the contact forces the rubber cups make on a package, how the deformation of those cups during contact changes airflow, and what happens if only some of the cups make contact. As shown in these videos, Gemini models the robot's arm and the robot's end-of-arm tool, which in this case is a vacuum gripper. These high-fidelity pneumatic and multi-body models enable developers to test a range of behaviors, like successfully grasping a package or dropping a package. Scientists and engineers can use these types of simulation experiments to calibrate and validate their systems. As another example, Gemini simulates how the robot's vision system identifies individual items in a pile of mixed packages, and how the robot's arm would calculate the approach angle and force needed to lift that package. Accurately simulating these type of real-world behaviors is challenging, especially given the millions of unique items that pass through Amazon's facilities. Consider, for example, a range of packages a robotic arm might encounter. They could include rigid boxes that hold a single immobile item encapsulated in cardboard or foam. Those boxes are much more straightforward to model. They could also include boxes that look the same on the outside, but contain a product inside that may shift its weight when lifted. Those are more challenging to model. Harder still are bubble-wrapped mailers that deform and shift to the center of gravity when they're lifted. Given the number of packages Amazon handles every day, creating one-off models based on empirical tests isn't feasible. Instead, we need to model the underlying physics of these interactions and verify those models against real-world data. Building and verifying these models is a massive undertaking. For that reason, Gemini leverages Drake, an open-source robotic toolkit created by MIT researchers and supported by Toyota Research Institute. Drake brings together several key elements for simulation. These include robust multi-body dynamic engines optimized for simulating robotic devices, frameworks and numerical solvers that enable us to create custom models that represent our real robots, and context solvers that calculate the forces that occur when a rigid body item interacts with other items in a simulation. Since Drake is open source, we're also able to dig into the governing equations, understand the underlying physics, and make modifications to meet our specific needs. Where possible, Amazon also contributes back to Drake in order to help the broader robotics community. Now let's talk through some of the open challenges and next steps. To bring the most value to Amazon, Gemini needs to close the sim-to-real gap as much as possible. One way we do this is by leveraging real-world data to validate the fidelity of our simulator. Another way we're looking to do this is by expanding the types of behaviors and items that we model. This includes modeling deformable objects, or things that bend, flap, twist, and sag. Some examples that come to mind would be stuffed animals or squishy pet toys. Both Gemini and Drake are actively working to model these types of soft bodies, but it's a challenging problem to solve. Despite these challenges, Gemini has already made an impact on the way Amazon develops robotic manipulation solutions. To give a couple examples, in 2021 and 2022, dev teams leveraged Gemini to troubleshoot costly field installations and performance challenges on Robin. Dev teams also used Gemini to quickly validate a robotic cart packing solution for the outbound duck process at fulfillment centers. The experiment showed the value of the idea, which is being implemented now. This concept validation would have taken at least 3 times as long if the team had to develop it on real hardware as opposed to developing in Gemini. So these are just a couple examples of how Gemini has already been impactful. We're excited to see how Gemini will further accelerate robotic development processes and help bring these solutions to Amazon facilities even faster, thereby making our Amazon customers even happier. Thank you all for listening. I hope you found this talk interesting and are excited to learn more about Gemini.